Hey everyone, so today I will be explaining the task number 2250 of leetcode, and the task name is count number of rectangles containing each point. So if you could read the task, you could get that it's a classic one, like it's classic sweep, and the task is basically, I will explain it here. Like let's say, doing this 1 second. This is the line, okay. So basically you are given 2 points. One is red points, let's say like this. Now these are the other corners of rectangle. Also you are given some other coordinates, let's say green coordinates. Let's say this is A, this is B, and this is C. Okay, so the question and the task was basically for each point ABC, count how many rectangles they were into. Like C is inside only one rectangle, and that is, let's say, we could also give name to this rectangle, let's say 1 2 3. So C is inside 3 and B is inside of rectangle 2 and 3, and A is inside the rectangle 1 2 and 3. So we just have to return the count for the task. Like for A answer is 3, for B answer is 2, for C answer is 3. So let's continue downside. Now the when you convert the task into like some mathematical language, so it becomes something like for each point let's say the point is, let's say, xi and yi. So we have to return the count of rectangles where r where let's say L only take, we could take the initial L is greater than equal to xi, and both conditions to satisfy, like and L, and let's say it is height, let's say it is greater than equal to yi, all the rectangle, because obviously if it has to lie, the it has to contain like what is the general formula for this to lie inside the range. Like let's say I want to check if 2 lies in between 3 to 5, right? So I could directly check if it is greater than equal to 3 and less than equal to 5, or this, either this, like x and y, or not x or not y, that is either less than equal to 3 or greater than 5, then it doesn't lie in range. Like either you could solve this or this. For 2D range, it is same thing, just that like if now the initial the bottommost rectangle coordinate is 0 comma 0 and all the coordinates are greater than equal to 0, right? So we don't have to check the left condition, we just have to check the right condition, that it is lying or not. So to lie inside the rectangle, it should be lying between the x coordinates and the y coordinates like this. So we could just check if 2 comma 2, let's say is 4, is lying in between 4 comma 5. Okay, so here we could say that like 2 comma 2 lies in 4 comma 5 because like 2 is less than 4 and 2 is less than equal to 5, right? Anyway, this is the basic stuff. I mean, let's get to the main stuff. So whenever there is written like count of rectangle, we could directly consider it as sweep. Now what is sweep? Basically sweep is basically either we could do sweep, but like we could also do some kind of modified brute force for it, because here they have given that x coordinate but y coordinate is less than equal to 100. So this is the main hint to solve the question, right? Remember that our task was count of rectangle. Let me borderline the task. This was our task if converted to simple language. So basically this constraint is very large. So whenever you see like one of the constraint is very large, getting approaching to 10 to 9, so obviously we can't store it in buckets or array or vector or something. What we could do is just like utilize this condition somehow, right? So if you see, let's say L is greater than equal to xi and H is greater than equal to yi, correct? So number of yi greater than equal to let me check one condition more, 2114, and what's the length of this? xi yj, okay, and point dot length. Okay, so it could be anything, and okay, cool. Okay, got it. So oh sorry, here now let's jump to like here, because okay, it is this one. So what should be our focus is basically for each point, let's say we are doing the brute force now. For each point P, how many rectangles are there? This is the task, right? So for each rectangle R, what we are doing is, let's say here answer is 0, and if inside P, if inside R, then we could do is answer plus plus or plus equal to 1, and there must be like some vector or array list or something, and we could just like push back to it, like let's say our vector is like vector int return, like answer, let's say answer could be more better. Answer. Okay, I'm reusing answer. One second. Vector int v, let's say. So v dot push back answer. Now this is basically brute force. This algorithm is whatever I written is brute force. If possible, pause the video and like try to calculate the complexity of this two for loops, nested for loops. Like, because like this for loop will run at most 10 raised to 4 times. Also this for loop will run at most 10 raised to 4 times. And I guess it's 2 into 10 raised to 4, I guess. Or 5 into 10 raised to 4. Okay, this is 5 into 10 raised to 4. So if you could see, these are nested. So something like each one should be like running for each one. So total complexity will be like R into C. So here basically let's say it is N and this is M. So brute force complexity will be becoming like N into M, which is nearly 25 into 10 raised to 8. Now if you see this is very large. Like at most in 1 second approximately 10 raised to 8 operations are allowed, and this is clearly TLE for the given constraints. Obviously it is solvable, but like not solvable under the given constraints, right? So what could be our target? Our target would be to like keep this loop same, right? And calculate, reduce this complexity, right? Now when, if you read the constraints, both the y coordinates are less than equal to 100, right? So you know that like for both, if y coordinate is less than equal to 100, you could modify the inner rectangle, right? Because like let's say you make the buckets like this 0 1 2 100. By buckets I mean vector list. Like whenever you see like there is something like this is apart from this, like whenever you see like some constraint is small like 10 or 100 or like anything like 10 raised to 5 also, right? It doesn't matter. Just like it's basically buckets. We could make list of buckets like here there are like 100 buckets, and 0 1 2 3 up to 100. And in these buckets are basically vectors, so we could store all the x coordinates that are into this, right? Now when we store the x coordinates, let's say it is like 2 1 5 1 2 5 3 4 5, it doesn't matter what is the range, right? Like we could compress the numbers, but like we don't need it. Like we could just push the numbers. Now what we could do is like we could sort the buckets. Like sort the bucket, I mean sort the vector or array, like sort 0 sort 1 up to 100, right? So what would be the worst case sorting complexity? It would be like summation of, let's say I is equal to 0 to 100 or max of y, right? But we are taking uh, up to worst case 100. Let's analyze the complexity later, like it would be like distracting now, right? Now what our aim was like to just optimize this to nested for loops, right? Because their complexity was going if inside this is the rectangle, you should get this right. This is not much hard. Like first for loop is for like point, and the second for loop is for checking each rectangle how many are there, answer plus plus, right? And the complexity is very large if you could analyze the complexity. So what our aim was like to just somehow improve this for loop complexity, not for loop complexity, but inside algorithm. Like if we could calculate answer more efficiently, then we could do it. So as I said, like hint was 100, so first make buckets and then sort all the elements like 1 to 5. Now how this sorting will help us, right? Now in various data structure, like sorting help us in various ways. Like the most useful and classic way is the binary search, right? Like let's say you are given an array 1 2 5 10, and these are the x coordinates, right, for given y coordinate. Like any whatever bucket is, like y is equal to 0, y is equal to 1. Okay, so we just have to calculate how many are greater than equal to the given point x, like whatever x coordinate of the point is, how many are there, right? So it's basically we have to find numbers in the range like px and infinity. Here infinity is basically 10 is to 9 plus 7 something, let's say, for the borderline. Now there is like one shortcut method, if you know that or no, I don't know, but just like if you want to find how many numbers are lying in the range, it's just upper bound minus lower bound. Like C++ has this inbuilt STL function, which is upper bound of like begin of v. You could see the syntax. I generally prefer all v because like and upper bound begin end of v and px. Oh sorry, this will be infinity, my bad. It's same as like how many numbers are in L to R range, so we could say that like there are total R minus L. This is based on the same concept that upper bound minus lower bound gives total number of elements in that range, right? If you see the syntax is basically upper bound begin of v end of v and like the element minus lower bound begin of v end of v and element, right? So this would give the number of elements which are lying in the range px comma infinity. Okay, cool. Now as we got this, now there are only 100 buckets, right? And we have sorted them already, like in pre-processing. Like how could we sort it? Like let's say for I is equal to 0 to 100, sort begin of v end of v comma, and this v is basically bucket of I and v, let's say, right? So we could sort it and we could find number of elements, right? So whenever you reduce the problem, like you could reduce it like you are solving brute force, and then optimizing the brute force somehow by looking at the constraints. Like here it was so small 100, so we could just use binary search, and the upper bound and lower bound are basically binary search, but we don't have to implement binary search, like we could use STL binary search. Okay, so now there are 100 buckets, right? Doing this same and counting the answer for each, like answer plus equal to for each lower bound upper bound, so we could get the answer, right? So what will be the complexity like this, like for each bucket we are doing, right? So let's say at most 100 are there, 100 into some log, correct? So what will be the complexity will be like size of like uh, size of like points into max of points, let's say 100 into log, and this log can be at most 10 to 4, which is around maybe 8 16 4 4 plus 10 cube is basically 10 cube is 10, log 8512, sorry, log at 256 10 1024,000. Okay, 1004 14 14 15 approx, like this would be like. So total complexity is basically this. This is the total complexity, which comes around like 10 is to 6 into log, which is feasible, hence go with it. uh, Now for like advanced version, like I will tell what we did again, like in summarization. Like first we implemented brute, second which was like 10 is to 4 into 10 is to 4 and into 25, so which was not feasible, hence we somehow try to optimize this, and then it got something like 10 is to 4 into 100 buckets each into binary search each, that is log, like optimization. But also this is the online method, I guess. No, sorry, not online, but online for points, right? And offline for like rectangle coordinates, like we should know the rectangle coordinate because we are sorting it already. And also I should add the sorting complexity for each. Let's say it should be like 100 into like whatever the worst n is, like n is basically, let's say 10 is to 4 into 5, so it should be like n log n, approximately this much. This could be, this should be the summation, but I'm not getting into complex stuff, I'm just like approximating currently, right? Okay, and this algorithm is online for points. And what does online means? Online is basically like the past queries are associated with, like current queries as associated with past point, yeah. So basically this point is not dependent on this point, but for rectangle, like we need all the coordinates because we are like already sorting it, so that total complexity is feasible. Okay, anyway, so now what we are doing is like we are taking the same question, just where is the straight line? Okay, Now we are taking the same question, and we are first there were like constraints were like xi is less than equal to 10 to 9 and the yi was less than equal to 100, right? So but now what I will do is I will make this as 10 to 9. So how would we solve this question now? Because like first yi was so small, so we optimized using buckets, but not right now, right? We have to somehow optimize 10 to 9 for 10 to 9. So first thing is clear, the algorithm is independent of yi, right? Or not independent, you could say, but like not much dependent on 10 to 9. Something like we couldn't use buckets or like something that could make use of this, right? Or if we have to make use of it, we just have to like compress the values, because like values are sparse like 1 8 10 raised to 10. But is it useful to like store it like this? We could store it just like we could compress 1 to 0, we could compress 8 to 1 and 10 raised to 10 to 2. Still relative ordering remains similar. Like when you compare 8 to 1, 1 is still less than 8, but you could still compare like 0 is less than 1. So why would you waste so much memory and all this stuff if you could store like this, if you just have to compare and not have to be dependent on the numbers, right? Anyways, so I will explain the sweep example. So now let's say we somehow have to implement the sweep, right? So if you saw my sweep video, so sweep video was basically we were somehow sorting the points, like whatever like question is, first sort the data, like whatever it is, sort it, right? Now like same thing we'll use, like we will use some kind of binary search, or we could use like some kind of data structure if we have the sorted data. If you saw my sweep video, I have shown already that whenever we insert point, we are inserting it in the data structure in continuous fashion, like 1 2 5. And if I have to deal numbers less than equal to 1, let's say this list is different, 2 is 3 is 2 3 5, and I have to deal with numbers like less than equal to 2. So what I will do is insert 1 comma 2 in my data structure, then less than equal to 3. But my 2 pointer, my pointer have already insert 1 2 in data structure, then it will insert 3, and then we go to 5, the my pointer will shift here and it will insert 5 to the data structure, 1 2 5. And we will gain, and we could until that like whatever query we are here, so we could just like solve in offline fashion and store the answer, right? And then just sort it, or like use answer mapping, like just like you make the array of answers, which is like n, and then you store whatever index is there, we could sort it like using sorting or whatever. Okay, so not let deviate from the point. This I explained just the revision of sweep, right? Let's jump to the advanced question now. Like we were discussing advanced question, but like I was just explaining sweep in between. Okay, cool. Sorry. Let's take the green pen. So I guess we don't need the number line visualization. It's simple that whatever sweep is as you see. So we just have to find number of xi for each xi number of L what are the H. Okay, so how many L and H are greater than a current xi by a, right? So we will use the sweep way, like let's say my xi array is 1 2 3 4 whatever, and my L is currently here 2 up to 2 up to 3. So if we could solve, like as I said, incremental way addition to data structures, we are doing here the same thing. Now we will just sort the data according to the x coordinate, and also we will either we could like compress the data like in 10 raised to 5 somehow, but I think compression is more better, right? By compression my constraints are now reduced to 10 raised to 5, or at most distinct values will be 5 into 10 raised to 4 into 2. So this will be, yeah, so 10 raised to 5 only, that's it converted to. Okay, so converted values after compression, my new constraints will be like xi is less than equal to 10 raised to 5 and yi is less than equal to 10 raised to 5, correct? So now what I will do is I will make vector of vector like bucket list, and here I will maintain 10 raised to 5 vector list, correct? And in this I will store x coordinates, same as we did in past, right? Now this is 10 raised to 5 after compression, correct? Now for x increment, for x in increasing order, right? Let's say our answer is this. Now what we have to do is we have to maintain a data structure which is storing y coordinates, or let's say because I have maintained this y here, so this will maintain the x coordinates, like data structure will maintain x coordinates because like buckets are of y. So for y is equal to 0 or whatever, like given queries, we could answer the queries all at once, right? This is little advanced, so like you should see my sweep video first, so like you could get a better understanding. So now answer, here it is the date. 1 second, I will use red pen here. Here's the data structure which is maintaining my x coordinates, right? DS which is maintaining x coordinate. So like you could directly binary search, either you could like maintain a sorted something, or like Fenwick tree, sorted set, or Fenwick tree, or segment tree, whatever you want to use, or try anything to calculate like some total number of elements, how many are lying in the range x to y. So either you, if it is a sorted set, you could use like upper bound minus lower bound. If it is, but it the complexity will be like log log, or either you could use Fenwick tree, or you could use segment tree and try. Fenwick tree is dependent on n, segment tree is also dependent on n, and try is dependent on number of bits. It will be like 30 bits. So you could use any data structure from this to calculate the answer. So now let's say this y is equal to 0. Now for the certain coordinate, like let's say we are coordinate and the list was like p points, let's say, and whatever this y is, we could directly add to the data structure, like for int x belong to like array or bucket of y add to the data structure x, right? Now we could just query our answer, like answer plus equal to query, or like answer equal to query only here, because like we are doing one time thing, we are using data structure to optimize the stuff. And whatever query complexities I have given here, like segment, if you use the set upper bound lower bound for let me just first discuss the range what we are finding. Like now we are given the fixed y, right? Now we know the y, right, because it is sorted by y. And for whatever int x we are doing this, we are adding it to the data structure, so we could find the numbers in the range for allowing this, right? So like what is the range? It is like infinity comma like whatever the current x coordinate is, right? So it will be, we are querying on the data structure. So in this way what we could achieve is like n into log, or depending on what is the query complexity, right? And don't worry about this, like whenever, even if you are iterating through points, total points are at most 10 to 5 only, so total summation complexity will be 10 to 5 only, right? So I think I should explain it again, or like give the gist of it. So what we have done was like we have changed the constraints, right? So for when we change the constraints, we just compress the array, like to change the constraint to like from 10 to 5, 9 to 10 to 5. And then I use the same algorithm as last one, like brute force, and then I optimize the inner one more, like instead of like traversing from 0 to 100, what I did was like maintain the data structure which maintain values 10 to 5, and we go in we went in like incremental order for like 10 to 5, and then solve for each points, and that's what we have to return, right? I should return it more clearly, this is more like confusing. Okay, so what we did was like for point p, these are sorted, just remember that. Also maintain a y coordinate here, let's say y is equal to 0, because like we don't have to like repush in the data structure, right? So while y is less than equal to point y, now for all the elements in the list in bucket of y, push element into data structure or add to data structure. Now you could easily query. Also remember that this is offline method, so you also have to maintain the indexes, like for when we sort, we lost the order which we have to return the answer, so we just like uh, we will also store some I with this, like if even if we sorted, this I will give the mapping to the original answer, right? We will store in pair everything, and then even if you sort it, so this is like I only, right? So query of like mapping of I will be our answer, which we will, or query from the data structure, right? Okay, then this is enough, I guess. I don't think so if we could like optimize it or like more or something, but this is the classic. Okay, I guess this is it, we should like stop here for this question. Thank you.